Right, it's my re-recording of 1.4.1. So part one, might be two parts if it gets too long. And we're going to go through all the sections in this video. So yeah, let's get on with it. Right, so obviously the primitive data types, I mean, at this point in A-level, you should know these 5 primitive data types. So I'm not really going to go through them. There you go, it's in the course, so let's just move on. Representing positive integers in binary, well, obviously, you should know by now that it goes 1, 2, 4, 8, 16, 32, 64, 128 and doubles continuously. And you just have a 1 below the numbers that you're going to use to add up to make the decimal or denary number. Very simple. Okay, not going to go on about that too much. So, right, how about negative numbers? Well, there are two ways, or there's not really two ways. There's one way and the wrong way, but you have to learn the wrong way. There is sign and magnitude. So yeah, basically that's it. So sign and magnitude, the idea was, let's make one of the bits represent a positive or negative. So if it's a 1, it's a negative number. If it's a 0, it's a normal positive number. And this sounds good in theory, you know, so this is 16, this is negative, sorry, this is 18, this is negative 18. But the problem is you end up with 2 zeros, because you can have a positive 0 and a negative 0, because we could have 0 and all zeros, or 1 and all zeros. And also the math doesn't work. So if we try and do binary math on these two numbers, for example, if we add these two numbers together, we're actually going to double the number and as a negative. So it's going to become minus 36, because 0 plus 1 will be 1. These will be 2. So we'd end up with a 1 in this column. These would be 2. We'd end up with 1 in this column. So we'd end up with 32 plus 4 to get 36, but it'd be a negative 36. So that doesn't work. The math doesn't work. So what do you do? Well, you use something called 2's complement. Okay, 2's complement is where essentially you flip all of the bits and add 1. Essentially, that's what you do. But you can think of it, I like to teach it as thinking of this first number as being a negative version of the number. So here is 18 represented positively, and here is 18 represented negatively. And if we were to add up all these numbers here, you would get minus 18. So you start underneath and sort of go up into it. There is an easier way to do it, and that is by flipping it and adding 1. So at the moment here, we've got 18. I'm just going to get rid of this little bit in the background. We've got 18 as a positive number, okay? Right, using 2's complement, but positive. So we flip it, and when you flip it, this is called 1's complement, okay? So this bit here, and I probably should put a little message there, is called 1's complement. So it is the flipped version of the number, okay? So you flip it to get it into 1's complement, and then you add 1 to get it into 2's complement. Okay, so we flipped it. That's the inverse of this. You've done a bit mask not, if you've got to that part of the course. And then you add 1. Like this, and when you add 1, you end up with this. The easiest way to add 1, by the way, is to, in fact, I'll just delete this. If you want to add 1 to a number, you can just find the first 0. So I'm going to actually make a harder number. Now, if I want to add 1 to that, actually I'll do it there. All I do is I go from the right, move across until I find the first 0, hit 1, and then I 0 out the rest. And that will add 1 to a number quite easily. So here, for example, I go across, put a 1, 0 out this, and then copy, then we've got all the rest of the numbers are the same. So here is the 2's complement version, and you can go back and forth. If I flip this and add 1 again, I will get 18 again. So if I paste that there, if I flip it, I'm going to paste it here so I can go on top of it, flip it to get the 1's complement, okay, then I add 1. There's my method to go across the first 0 and do that. And you'll find this is 18 because this is 16 and this is 2. So this is the negative 18. So basically you flip it and add 1 every time to go back and forth. There you go. So, right, binary addition and subtraction. Okay, so, yeah. Let's do it. If a number goes over the maximum significant bit this end in a binary addition, it's called an overflow. If it goes over this end, it's called an underflow. And let's get on with binary addition. Okay, so let's do 30 minus 11. Okay, so essentially we're going to do 30 plus minus 11. That's the easiest way to do it. So, and if it was obviously minus a minus number, you would just, add 11, right? And obviously you know maths, I'm sure. So anyway, so we've got 30 here. So we've got to make, I'm actually going to change that just to 1's complement. And then I'm going to put 2's complement in here, just so that you all know that in your head. That is what those are. Oh, no, not there. But I'll put it in there. I'll move it. It's big. There we go. So obviously we've got 11. Then we flip it to make it 1's complement. Then we add 1. Here I'm doing it with the +1 and actually doing the binary math. But again, remember, you would just find the first 0, put a 1, and then put zeros all the way along. But obviously this is an easy one. And then we end up with the 2's complement version. And then we add the 2 together. So this is 30 plus minus 11. So 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0 carry 1. No, yeah, 1 plus 1 is 0 carry 1, which I haven't got here for some reason. So I'm just going to put there a little 1. There we go. 1 plus 1 is 0 carry 1. 1 plus 1 is 1 carry 1. So I'm just going to put a little 1 there. I don't have my pen with me, so I can't draw on it, annoyingly. And then 1 plus 1 is 0 carry 1. And then 1 plus 1 is 0 carry 1. And then 1 plus 1 is 0 carry 1. And obviously a number that goes over the end is called an overflow. But in fact, that's useful in this case because it knocks a 1 that we don't want out of the contention. And then we're left with 19, which is 30 minus 11. So yeah, so the binary math works, okay, with 2's complement. So if you want to add, do a negative, you just add the number to it, and add it as a negative version. There we go. That's basically it. Right, I'm not going to go through binary, decimal, and hexadecimal in this video. It's in my J277 playlist. I suggest if you need a recap, you go through that. The only thing, I can leave this screen up, which does sort of explain it to you. I'm going to show is a sneaky little thing I saw in one of the exams, which is where they don't have like a multiple of 4 number of digits. So let's have a look at that. I think that's got 4, 4, and 2. Okay, and essentially what you've got to understand is this is actually these digits. The right 4 for this one. Then there's this one, and then there's this. And that's actually how you break it up. You go from right to left. So obviously this is going to be 8, 4, and 1, which is going to be 13, which will be a D. This is going to be simply 7, because it's 1, 2, 4. And this is just 3, okay, because it's just 1 and 2. And you can presume there were 2 zeros at the front. But obviously you can't skip that 0, but you can skip the zeros here. So just be a bit cautious of that. Yeah, I could have done hex to bin, bin to hex actually, couldn't I? I just realised that. Used a built-in formula. I don't know if it'll work on this one here, because I used a special symbol. It is going to work. There we go, yeah. But anyway, obviously I haven't got that in the exam. So just remember that it goes from right to left. Yeah. Right, so floating point numbers. Okay, this is where it gets a little bit more tricky, but this is fixed point. Okay, so right now we're going to talk about fixed point. And what that means is where you allocate a certain number of bits for the whole number and a certain number of bits for the fraction. So here we've got 4 bits for the whole number and 4 bits for the fraction. And how it works is it just carries on. It's nothing clever. It keeps on halving as it goes down, and it halves like this. So obviously, as you can see here, this is how we represent 14.8125. We have 14 there, and then obviously these add up to 0.8125. It can get quite tricky math, and they will require you to do something like that, maybe even with 130 seconds. So be prepared. But this is quite easy because it's fixed point. It doesn't have to be 4 and 4. It could be 2 and 6. It could be 6 and 2. But obviously, the more bits you've got for the whole part gives you a higher range. The more bits you've got for the fraction gives you higher accuracy. So higher accuracy in the fraction, higher range. Obviously, if we move this 2 across and we stick it here, then we only end up with 2 and 1. And then, of course, we've got much more precision in how accurate our fraction part can be. But at the same time, I can't even do this math, but that would be something like 2 plus 1.18 plus 1/16 plus 1/64, which I'm not doing live because I can't bother, and that's really annoying. In fact, I just missed out a half. That's also a half. I don't like the way it's done that. Yeah, there we go. So that's actually a half plus an eighth plus a 16th plus a 64th. That's going to be a lot. So that'd be 3 point, whatever, something like, 6 something. In fact, I could probably just put it in Google. I'll just put it in the Google. Good old Google. Put it in there. It is in fact, well, okay. It's come back as this. So there you go. Oh no, I've done 1/6. I didn't put 1/16. I did think that looked odd. There we go. Let's do that again. I was going to say it shouldn't be that many decimal places, and it should have a lot of rounder numbers. But there you go. Oh, somehow I've managed to go onto a new page. That's what the answer is. It's 3.703125. So let's hope they don't ask you to do 1/64th, because that'll get quite annoying. I'm sure they won't. They might ask you to do that. Maybe if it's just that and that. I don't know. I mean, it's hard to know. There have been some tricky ones. Anyway, so that's fixed point, where you've got a fixed number of bits for each side. So here, okay, remember we've changed 2 for the whole part and 6 for the fraction. Okay, so I'm just going to undo all that so I don't save it. I can't go back further than that, so I'm just going to put it back. Right, so there you go. Range, accuracy. Bigger number of bits here, range, bigger number of bits here, accuracy. Right, now that is one way, fixed point, but reality is computers actually use what's called floating point numbers. And there's no predetermined number of bits used, but because it doesn't work that way. It's done very similarly to it's done with scientific notation, where like it's like m to n 10 to the power of n, but of course it's 2. But let's not get too much into it. So basically, you break up the number into a mantissa part, which is the actual number, and then the exponent, which is how much you're going to move the decimal place, basically. So it's probably best shown by example. So let's go here. So example, using 12 bits, 8 for the mantissa. So this is the actual number, and this is the exponent, how much we're going to move the decimal place, basically. In fact, I'm going to copy this into Excel and show you it a bit better in here, because I think I'll do a better job. So we've got the exponent, which, by the way, these numbers are linked, but they don't sort of, what I mean is, once you work out the exponent, like this bit, it's dead. In fact, I'm going to cut that and put it in here so that I can actually delete it. So I'm going to put error. Right, so this is the exponent and this is the actual number. So currently the number is 2468 digits. So let's stick down the digits separately. Right, but we've got the full stop here, which I'm going to put there. I don't know what I did there, and then put it to the right because I can't do anything better than that. So that is the full stop. Actually, I can put it at the bottom. Top. Absolutely total. Small. Okay, I'll just stop there. Anyway, the dot's there. Right. So at the moment, the number looks like this: 1/2. Quarter. Actually, I could have just done over there, but let's not go into it. 1/16, 32nd, 64th, 128. Right? But I'm not going to calculate what that is because longer math and stuff. So, but we've got this exponent, okay, and this exponent adds up to 3. So we've got 1, 2, 4, 8, okay, and it adds up to 3. So the exponent is 3. So what that means is we need to move this 3 across to the right. So the decimal point moves 1, 2, 3. Now it's here. Okay, well now these don't mean these things anymore. This means 1, 2, in fact, you know what, I'm going to be smarter than I look. And I'm going to move that there. Okay, this means 1, 2, 4, 8. And this means a half, a quarter, an eighth, and a 16th. So now we've got the number. We've got this number is 5 point. I'm just going to do the rest of it here because so it's 0.5 plus 1 over 8 plus 1 over 16, which is going to be that. So this number would be 5. In fact, I'll just add 5.6785. That is the number here represented. It's going to be that same size. So 5.6785. And you might have to do that math. You might have to add up. The best way to do it, I think, is to do like 0.5, do 0.25, do 0.1625. You know what I mean? You know, and then so on and forth. You know, 0.08625. So that's 2. 8125. So my math is terrible. Yeah, of course, it's half of 25, isn't it? 12.5. Yeah, so like that. And then you would have to sort of add them up. Yeah, just don't make the mistake. I mean, I don't think you have to go much past 1/16, but who knows? They could. You know, hey, it's A level, so you know that's the reality. So that is how you do that. I could do another one, very quick example. Let's just pick some random numbers. 0.101011246 yeah, and then the exponent could be 0110. All right. It doesn't mean I'm going to be able to do this math, by the way, because I might have given myself a number that's nearly impossible to do mathematically. So obviously it's 0, 1, 0, 1, 0, 1, 0, 1, and the dot is currently here. It's quite handy that it's on a cell. So the first thing to do is work out the exponent, because really this doesn't matter once you do that. So this is 6, and that's now dead to us. I'll just leave it. I'll highlight it. So that's dead. You don't need to. That doesn't affect that anymore. Once you get the number out of it, you don't need to worry about this anymore. Bye. Okay. You just know that's 6. So now we move it over 6. 1, 2, 3, 4, 5, 6. So now we've got a nice easy number. So this is 1, 2, 4, 8, 16, 32. Might as well stop. And this is 1 over 2. This is a half. 0.5. I mean, you might want to get into the habit of writing 0.5 and writing these out. It might help you later on, so you just learn the math of it. Maybe, I mean, I don't know, it's up to you. Anyway, so this is 30, 40, 32, 40, 42.5. Let's double check that because I am prone to making lots of errors in these things. But yeah, so that's that one. Yeah, it's 42.5. And that's basically fixed. That's the simple floating point number with an exponent and a mantissa. So this is the mantissa, this is the exponent. So I'm just going to recap again, just in a quick slide. So basically, the steps are, if you've got a positive mantissa and a positive exponent, you work out what the exponent is. That's 3. So we move it, we worked out that's 3, and then we don't worry about the exponent anymore. It's like dead to us. The exponent, just work out what it is, and then you don't worry about it ever again. Here it's 3. Then, of course, we move the decimal point that many times, and then we simply map it out on a normal number line, including any fraction parts that you need, and then you work out the answer. So it's nothing too amazing. If they're both positive, it's quite easy. Okay, so here's where it gets a little bit more annoying. It's not horrendously annoying, but it gets a little bit more annoying. It's how to handle a negative exponent. We'll start with a negative exponent, so this one here. So, okay, if it's a negative exponent, you know that because it'll start with a 1. And this is a positive mantissa. Okay. So basically, you need to work out what the exponent is, as always. Now, obviously, you flip it and add 1, or you can just count this as -8 plus 4 plus 2. So if I flip that and add 1, then, of course, I'm going to get 2, -2. So I know that's -2. You can work it out, but I just know that's -8 plus 4 plus 2. Easiest way, really. But you could flip it and add 1 and work it out the normal binary way. But it's -2. So now the difference now is, before we would move it 2 to the right, but now we've got to move it 2 to the left. So here we've gone from there to there to there. We've now moved it 2 to the left, of course, and now we map that number out on a number line like this. And then, of course, we get minus. Remember, that's a minus. No, it's not. Sorry, this isn't a negative mantis, so ignore that. Remember, that's a yeah. So we just map that out normally and add it up. Okay, it ends up being 16. So I'll do another one with a in Excel. Let's do another one. Let's do this. Let's go. Okay, so let's just try a random number with a negative exponent. So let's start with 0, 0, 1, 1, 0, 0, 1, 1, whatever. Right, there's our mantissa. Okay, it's a positive number, but I'll do negative mantisses in a minute, although that doesn't actually make much difference because we just turn it into a 2's complement version. But anyway, 1, 1, 0, 1. Okay, so that ends up being minus 8 plus 4 plus 1. So that is minus 3. Okay, this time we've got minus 3 exponents. So you can, let's map this out properly. 0, 1, 1, 0, 0, 1, 1. Excellent stuff. And we've got our dot, which I'm going to use a star for now. Because, I don't know, reasons. Right, so that is what it currently is. But now we have to move it 3 to the left. So we have to go 1, 2, 3 to the left. Like this. 0 there. Oh, I should have. In fact, I'll copy this. In fact, you know what I'll do is I'll put that back. So we can see the original number, and I'll bring this down here. And then, so it's gone 1, 2, 3. Obviously, we've got a 0 here because this was like it's on that one. Actually, no, I'll just do that. Center that. Center. Right. So now we've got to put 3 zeros in here. So it's going to go 0, 0, 0. 0.0000 because we've got to put 3 zeros in, and then 1, 1, and then it would be 00, 2, 4, 6, 8, like that. Okay, now it does mean here that we have lost some data because we just don't have the precision to hold it in this 8-bit. And this would be an underflow because we've moved these over and lost these. It's very unlikely you would get that in the exam. And then, of course, you would map this on a number line and find out that it's 1/2, 1/8, 1/4, 1/16, 1/32, and 1/64, which I'm definitely not doing. But yeah, so just remember that's what would happen. You would lose that because you've only got 8 bits. Right, so there you go. Let's do another one. I'll still leave it. I'll make this minus 2. So I'll do that. So that's minus 2, and then I'm going to do that so I get one that doesn't underflow. 2, 4, 6, 8. Right, here we go. So I've got 0, 0, 1, 0, 1, 0, 0, 0. Rogue. And then star for the dot, which I'm going to put here. And now we've got to move it 2 to the left. So actually, the easiest thing to do would probably just be copy those 2 down there. Fill those with zeros and then leave the star where it is. Maybe that's easier to for you to understand. I don't know. But essentially move it 2 over like this. 1, 2, 3, 4, 5. So 2, 4, 6, 8. So we'd lose those 2, of course. And then we would end up with that. Okay, so the numbers are moved. The dots moved over to the left 2. And then, of course, any lost here would be lost. Luckily, there were zeros. And, of course, this would be 1. And then, you know, 1/2, 0.5. In fact, I could just do this /2. And then, you know, what would this be? It would be like that. And it would be 1/2, 16th, and 1/64th. Point, blah, blah, blah. Okay, there we go. That's the reality of it. There we go. So that is a negative exponent, positive mantissa. Now, what if we have a negative mantissa and a negative exponent or whatever? If you have a negative mantissa, it's best just to convert it with 2's complement into a positive number. So let's take this. So now we have a negative number, right? So the best thing to do, so let's say we've got a negative exponent, but if you've got a negative mantissa, one of the easiest things to do is turn it into a positive number before you do any shifting. And then just remember that it's a negative number. Whether there's a negative exponent or not, I tend to just convert it into 2's complement version of it and then carry on. So let's just do that now. So this is a negative version. So we flip it and add 1. So we end up with 0, 0, 0, 1, 0, 1, 1, 1. Okay, so that's the 1's complement. And now for the 2's, I'm going to add 1. So that ends up being find the rightmost 0, which is this one. Turn it into a 1 and then fill with zeros. Okay, I'm just going to double check that. Flip, add 1, flip, add 1. Right, so that's the 2's complement version. Okay, so now it's 0 dot, like that, obviously, you know, in theory. Put these in, you know, imply these are there, infer these are there, sorry. And then we've got -2. So then we just do the exact same thing, but we just remember that it's a negative number at the end, right? If you want, you could flip it and add 1 again, but you don't need to. You just need to understand that it's a negative version of the number. So, of course, we move this 2 across. This becomes 0.000011. Nope, because we've moved it 2 over. It's removed the at the end because I didn't keep it as a text, which is why I'm putting this little apostrophe there. It stops the computer removing zeros and stuff, or editing anyway. It does put this annoying arrow that you have to keep ignoring all the time, which is quite irritating. But anyway, so yeah, and then you would calculate what this is normally. Of course, that's a really irritating number. I don't really want to do it because it would be equal, you know, it's 0 dot here. So, you know, this is going to be 1/8, 1/16, half, quarter, 8, 16. It's 132 plus 1/64. But just remember that it would be minus. So it'd be minus 132 plus 1/64, and that would be the number. Like that. And that's what it is. So if you've got a negative mantissa, just make it positive and then just do everything as normal, and it's a lot easier. Right, so there's a problem with this notation though, and this is why we need to do something called normalization. So I'll just go through the problem and then we'll talk about this. So this is the problem. All this is in normal deanery, right? Normal deanery that we use. And this is scientific notation, but these are the same number. So that and that actually equal the same thing. And that's annoying. Also, for example, look, we've used 4 digits there. If we had this number, we've got some more accuracy that we're losing because we don't, you know, we're using these digits here and we don't need to. So normalization gives us the highest level of precision because it gives us the more levels of digits to use in the decimal part of it, in the floating part of it, the actual fraction part of it. And also, it's not a good idea to have different ways to represent the same number. Like, you couldn't check if those numbers were equal because technically they're different numbers. Like, they add up to the same thing, but that's annoying, right? So this is a process called normalization, okay? So how do you know if a number is normalized or not? Well, a positive number will have 0.1 and a negative number will be 1.0. Because remember, that's going to be flipped and that's going to be flipped, so it's going to end up as this. So that's how you can think about it. It's really always going to be 0.1, but of course a negative number will be flipped. So that's basically it, really. And that way you haven't got any wasted zeros here. Because remember, we're going to move the decimal point. So if there was a 0 here, why don't we have it next to the 1 and move it 1 more? Like, that's the whole point. So let's take this number here, which the eagle-eyed of you will see is 3.5. Okay. So this is a positive, normally a positive binary number. It's slightly different. I'll go through the processing of one in a minute, but let's just do this one. So 3.5, okay? So essentially, we want the dot to be here, right? Okay? So we've had to move it 1, 2 across, like that. So it ends up here, right? Now we've moved it 2 to do this, right? Moved it 2. So because we've moved it 2 to the left, to fix it, we'd have to move it 2 back to the right. So our exponent is going to have to be 2. So then we have a number. Our mantissa becomes 0, 1, 1, 1, right? And our exponent becomes 2, 0, 0, 1, 0. And so if you look at that number here, right, let's take it up here, 0.111, and our exponent is 0, 0, 1, 0. Okay, this is normalized now because there's no inaccuracy here. So let's work the exponent out. The exponent is 2, we know that, right? So then we've got 2, delete the exponent. Move that 2 over, 0, 1, 1.1, okay? Don't worry about any preceding zeros. So that's a half, that's 1, that's 2, and we end up with 3.5. So that is how you normalize a positive binary number. It's not very difficult, just a bit tricky to remember it really is the difficult bit more than anything else. So you need to count how many times the 0 goes across until the dot goes across until it meets the 0 really, until it sits between a 0 and a 1. And then that's going to be your exponent, okay, and that goes in your exponent thing. And then obviously just write the number out as your mantissa. Simple as that, really. And then it's 0 point and then 1, 1, 1, and any trailing zeros don't count. So obviously we lose those. And so the number is just 0.111, 0.111, and then the exponent is 2 as directed. Right, so before I showed you writing out a binary number normalized using a mantissa and an exponent, but they do often give you as an exam question like one not normalized and ask you to normalize it. So here is one already in a mantissa and an exponent, but it's not normalized. And we know it's not normalized, of course, because this is not 0.1. Okay, so we need to make it 0.1. So obviously what you've got to do is move the decimal point to where it is 0.1 and count. And so we've moved it 1 to the right. Now, if we've moved it 1 to the right, remember the exponent will move the digit to the right, okay? And because we've already done that, if we move it 1 to the right here, we no longer need to move it 1 less to the right later, okay? So we need to take 1 off. So every one you move it this way here, you minus over here, okay? If you move it that way, you add over here. Basically, that's the simple answer. So so we've moved it 1 to the right. So we then end up with 0, 0, 0, 1 and 0, 1, 0, 0. But of course, these don't count, and of course, they're not relevant. But you can see now how we've got more precision here now than we had before with the same number. Okay. And that's basically it, yeah. And if you work it out, you'll see it's the same. So obviously they had 0, 0, 1, 0, 0, 0, 1, 0 as the exponent. So they had 2. So where was the decimal point? So they would end up with 1, 2. They would end up with 1.000, doesn't matter, right? Whereas in our version, which is the improved version, the normalized version, we have 0.100 and an exponent of 1. Okay, so we cross that out, we move it over by 1, and we both end up with 1.000000, whatever, cross out 1.0, but ours was in a normalized format. So essentially, if they give you a mantissa and exponent and say, is it normalized? Look to see if it's if it's 0.1 or 1.0 for negative numbers, but we'll go through that in a minute. Look for 0.1. If it's not, move this point to the right, it'll be to the right. By how many it needs to go, count that, and then just deduct that from your exponent, and that's it. Yeah, quite simple, not too hard. Okay, so what about normalizing a negative binary number? Right, well, here we go. So we know this is not normalized because, I can't write like that, because it's not 1.0, which is what we want. So we move this 2 to the right to get it to 1.0 here. Right, but we've moved it 2 to the right, and again, we've got to make this smaller by 2. And it's on 1, so we need to have 1 minus 2 equals minus 1. So we've got to represent minus 1. So to represent minus 1, you write out the number and flip it and add 1. So that's already the number because we want minus 1. So 1, 1, 1, 0. Add 1 ends up being 1, 1, 1, 1. So that would be the exponent, okay? And then the mantissa would be, where is it? 1.000, like that, because we've moved it 3 over to the left, and yeah, there we go. That's basically it. Not too difficult to understand. And there you go. We can flip it back and get it to where it was before. But there you go. That's basically what it is. Okay, so now we're going to look at adding together two binary numbers. Now, if you don't know how to add together two binary numbers normally, then do check out my GCSE video, J277 playlist. You can see binary addition. I'm not going to go through the basics of binary addition. You could probably work it out from here. But anyway, so let's take these numbers that are normalized. Let's just make up some numbers. There we go, 1101. Right. But the problem is they're going to have different exponents. Sorry, so I'm just waffling as I think about what numbers to do. Let's do 0010 and 0011. Okay, so this has got an exponent of 2 and this has got an exponent of 3. So we can't add these together because the exponent, they're not actually these numbers because they're going to move. That dot and that dot are not actually going to be there. This one's going to be here and this dot's going to be here. And we need the dots to line up, don't we? So you could just shift it till you get them to match, like move this down 1. So that's 2 and 2. I'm just going to, normally people just get them down to non-normal, to, you know, expand them and then do them together. So let's do the first one with the 2. So if we put, let's just move this up. Okay. So obviously currently you're thinking of this as 0 dot and what happened there? 0 dot, and you're thinking of this as 0 dot like this. And of course this exponent is 2, so it needs to go 2 to the right. So these need to go 2 to the left. So if we assume that the numbers move, we're going to end up with, if I paste that there like that, except get rid of that dot and put the dot there, which means I'm going to have to press apostrophe, otherwise it won't do the dot. So I end up with this 1 O and then obviously O's. Now of course we would lose the precision at the end, so don't worry about that now. So then we have to do the same thing with this one here. Right, so we'd of course lost these 3 like that. End up with that. Now we've got to do this one. Move these 3 across. 3, 2, 3. Put the dot here. So I'll get rid of the dot. I have to put that in. There we go. The dot's moved over 3. And then we end up with that. So now we've got 2 numbers back where they are. And then of course we can line them up. The dots. Add them up. So 0 plus 0 is 0. 0 plus 0 is 0. No plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 1. 1 plus 1 is 0 plus 1 is, sorry, what am I doing? 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. Decimal point stays there. And obviously 0 plus 1 is 1. 0 plus 1 is 1. And 0 plus 0 is 0. And of course we need the 8. So we take those 8. Lose any preceding zeros. Yeah, there you go. That is how you would add those 2 numbers together. If in binary arithmetic. So the step is get the exponents the same. You could just do it by getting the 3 to the 2 or the 2 to the 3, but it is easier probably just to expand them completely out, add them up, and then take the 8 bits or whatever you're allocated to as the final answer. Right, so now we're going to look at something called logical shifting. Okay, so here I've written out, ignore this bottom part for now. Here I've written out the number 111. Okay, so it's written there, 111. And we're going to do a logical shift, which is moving the bits left or right. So we're going to do a logical shift right. And so basically, if we move all these down 1 to the right, okay, so we would end up with that. And then whatever falls, so this goes right, 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 right. Whatever falls off the end goes into the carry bit, like this. And then you fill up any gaps with zeros. And what you can see there is I've basically halved the number. Okay, so when you shift to the right, you halve the number. However, you may notice, the eagle-eyed of you, that that's not quite the same. Because if I double this number, I'm not going to actually get back to this number. So if you logically shift right, and then left, okay, you don't come back from that. It doesn't come back in, okay. If we did a left shift now, we would in fact, let me copy all this, we would in fact have that goes 0, and what went off this end would now go on the carry bit, and so 0 came off this end, and so 0 would go back in there. So you can see that a logical shift left doubles the number, a logical shift right halves the number, but it will round down. There'll be some rounding in one way or another. Even if you have floating point, there'll be some rounding at some point where it rounds down something. Okay, so that's what a logical shift is. Logical shifting is just used to shift numbers around to do like multiplications. Okay, now let's look at arithmetic shifting. So it's the same thing as before basically, but because we have a 2's complement number, we have to factor in something. So shifting to the right, well, a very similar thing before. Everything goes over 1, so they all go to there. That goes into the carry bit, right? But before we put a 0 in there, okay, and that doesn't work because it's 119. Now we copy down the sign bit. We preserve the sign bit. So that was a 0, we'd put a 0, but as it's a 1, we put a 1. And now what you can see is that I've got halves but rounded down again, because that's what happens. It always rounds down. So we've actually, yeah, so just remember negative numbers, essentially you're going further the other way, but that's because it's negative. But anyway, it is what it is. It rounds down. And then of course, if now we do the opposite again. So we've done a right shift. So now we can do a left shift. So this all goes, what would go across 1, right? But that's not how this works. Basically, you have to think of this as a protected box when you go left, and you skip it. So this will actually skip into the carry bit, and then these will all skip into here, and you fill with zeros. Okay, so you go over the sign bit. The sign bit is protected. It's protected. It's protected here, and it's protected here. Okay, so it's protected here in that it doesn't change. You can't touch this one. It doesn't really exist. When you shift, you just shift over it. You can use it to copy to things, but you shift over it. And obviously in a right shift, that doesn't matter because you don't actually touch it. You would just try to write a 0 on it, but you can't because it's protected. And on a left shift, you skip over the number. Okay, so let's do a different number, and we'll do a right and left shift. In fact, I'll just do a right and left shift of the same number. Okay, so let's do that. We actually can't do, actually, I'm not going to do that number because it's actually minus 130, so it'll be too big to be properly displayed with 8 bits. Right, so there we go. So we right shift, okay, so right shift as normal. We copy over the numbers, and as we run out of numbers, we write the next one in here, so that's 1. I'm going to delete that one for next time. Of course, and then we look up here to copy down the bit, and we copy it there. Okay, now I'm going to do a left shift of this number, not this one. I'm going to do a left shift of this number here. So I'm still doing a left shift of this. So with a left shift, that is going to skip over into there. Okay, so that has gone into there. And then these all go over 1, but you still fill with zeros. And of course, the sign bit is protected as always and gets the correct answer. So that's how you perform arithmetic shifting. And it's the same thing as before as to why you do it. You halve a number or double a number, and there you go. So you could say, let's say, for example, I'll do some easy ones, and then I'll do a hard one. Let's use this to show you what the point of it is. In fact, I might as well just delete this here. And then use it. So, what's the point of the shifting? Well, let's have a look. Let's ignore the carry bit because essentially the carry bit is only used to know whether you've got an underflow or an overflow. It is used in other situations in a minute, but right now that's all you got to know. Let's say, for example, we want to, I don't know why I deleted that. Yeah, I was going to say that's quite handy. Let's say we want to do minus 25. Actually, I'll just do normal 12. I'll do a normal one and then I'll do a negative number after. Let's do 15. Let's do 15 times 5. Okay. So the problem is, actually, I'll do times 7 because it's a more interesting one. Can we do 15 times 7? Let's do 11 times 7, because we can definitely do that with the number of bits that we've got. Actually, I think we could have done 15 times 7. Yeah, I just realised we could have done this 105. But anyway, let's just we're doing 11 times 7 now because, hey, here we are. Now, the thing is, computers don't do times the way you do. What they'll do is they'll do shifts. Now, when we go left, we double it. So what you want to do is, what's the highest power of 2, sort of like, that goes into there? So I can do a left shift of twice, and that will give me a times 4 number. Okay, so let me show you what I mean. So if I left shift twice, so once I end up with there, that's not going to allow that. Let me, so F4, F4, F4. To lock those, drag that down, 44. So now I've got one that is 4 times bigger by left shifting twice, right? Now I've still got 3 to go. Now I can left shift once to get a times 2 one. Left shift once. Okay. Doesn't matter about arithmetic or logical because this is a non-negative number, so it doesn't really make any difference at this current time. And we're not got any ones coming over here. So that's 22. And now I add them all together because I've got a single version. You know, that's worth 1, obviously. That's worth 4, that's worth 2. And that's how I can do it. So add these up. 1 plus 0 plus 0 is 1. Oh. Okay. 1 plus 1 is 2. So that's 0 carry 1. I'll put the carry, because I can't think what to do. I'll make it really small. 6. That, put it at the top. Can't think what else to do. So 1 plus 1 plus 1 is 3. So that's 1 carry 1. Okay, 1 plus 1 plus 1 is 3. So that's 1 carry 1. Okay. 0 plus 0 plus 1 plus 1 is 2. So that's 0 carry 1. Again, that's 2. So that's 0 carry 1. Okay, that's 1. And that's 0. And then you'll see there, unless I've messed this up, that I get 77. And so by performing a section of shifts, that is how you would do like minus times 7, sorry. And yeah, that's basically it, really. And you could do the same with negative numbers. If this was minus 5, let's do minus 5 times 7. Actually, let's do minus 5 times 11. Or should I do that? That'd be quite a lot of them. It's only an easy one, isn't it? So minus 5 times 11. Okay, so then I've got to figure out what I want. And I want, now I know it's powers of 2, like 1, 2, 4, 8. I want an 8, a 2 and a 1, don't I? That's how I'm going to make 11 out of powers of 2. Out of these numbers, basically, how can I make 11? So I need, let me delete all these. So I need to get an 8 times number. So I need to shift this across 1, 2, 3. So that's a left shift of 3. That's a left shift of 1, and that's a shift of 0. So obviously I'm just going to, not use that. So I'm just going to take this as being the 1 version because obviously it all. So I have to left shift 3. So 1, 2, 3. So that's going to skip over. So 3 across. So you're going to go 1, 2, 3. So it's 1, 0. Oh, 1, 1. Sorry, 1, 1, 0, 1. And then of course we skip over this. So that stays as 1. Okay, and look, we've got minus 40, so that's worked because that is 8 times 5, minus 5. Then we want to do a version of 2, so we go 2 times 1, sorry, so that's a left shift of 1. So 1, 1, 0, 1, 1, 1, and then we skip over and we're finished and the rest overflow. So that's minus that, of course. And then we add them up, which is 1 plus 1 plus 1 is 0. 1 plus 1 is 0 carry 1. I can't watch the little one. Oh, it's remembered it. Brilliant. That's 0 carry 1. That's 1 carry 1. Now we've got 4 here, which is good because I was hoping this would come up. Because obviously now I need to carry 1 over here and put 2 and then 0, 0. Obviously I'm carrying a 0, but there's no point doing that. So it's 1 plus 1 and plus 0, 1 plus 0 plus 1 plus 0. So that's 0 carry 1. But now I'm carrying 2. Okay, because obviously I was carrying 1 before. So now it's 1 plus 1 plus 1 plus 2, which is 5, right? So that is 101. So that's 1 carry 0. And then obviously the 1 is lost anyway. And then this bit is always preserved. So we just add them up anyway, and we get 1 carry 1, and there we go. And all the bits over here are lost, and we've got minus 55 as corrected. I doubt you would get one as hard as that in the test. I think it'd probably be something like 10 times 6, 7 or something, or whatever. But there you go. That's how you can use shifting to do multiplication. So we'll look at the last shift, and that's circular shift. So basically, let's say I have some numbers in here. Oh, and we've got a 1 in the carry bit. Same. A circular shift. If I performed a circular shift right, then basically everything just goes around in a circle. It's kind of obvious. I'm assuming you worked that out. So obviously, I'll draw the carry bit out afterwards. Oh, look at that top quality drawing. Obviously, everything would go down 1011, 0110, and then what was in the carry bit would go all the way back over here and end up back on this side. Okay, so that's all a circular shift is. Everything just gets shifted round, and what was in the carry, and if it was going left, then don't forget that you would pretend, if we were going left, sorry, you'd pretend the carry bit was like over here, and then everything would go into the carry bit and then round back this way. So the carry bit sort of doesn't actually sit on the right or left, it just sort of theoretically. That's why I sometimes draw it in the middle actually, and then just go like it goes from there into there, or there into there, into there. It depends on which way you're shifting. Look at that top quality notes there. But yeah, that's a circular shift, nice and easy. Now, what is the point of a circular shift? Well, it's quite handy when you're working across multiple bytes. Let's say you've got a really old computer and it's only 8 bits. Right, that means each memory address is only 8-bit. A memory slot is only 8-bit, but you want to shift across the bits. How do you do that? Well, let's say you would use this. So you would, let's say you want to, halve both of these. Let's say you're counting these as a big number because you're using two bytes to store it. I'll just put any old numbers in it. 1. We could perform a right shift on this one. And then a right, say you want to halve this. Say this is a combined number. We're using this to store a bigger number across 2 bytes. And then right. So if we store right here, this will go 0, 1, 0, 1, 0, 1, 0, 1 in there. And then we perform right. And now this one uses the carry bit. And so this one would go 1, 1, 0, 1, 0, 0, 1, 1. And then obviously 1 would eventually end up back in the carry bit. But then we've managed to sort of send data from one block across to the other using the carry bit as sort of temporary storage. And that's basically how you do it. Okay, so I'm just going to look at the last bit, which is an easy one, which is bitwise masking. So it's quite similar because you know how these work already. So you just perform it on a bitwise level. So you go down. So obviously with a not, we would completely and utterly flip what that is like that. With a not, with an AND gate, you would, that would be a 0 because they're not both 1. That'd be a 0 because not both 1. That'd be a 1. That'd be a 1. Okay, so you're performing an and getting a new number. This can be quite good for doing like turning motors on. Let's say you wanted to turn on, let's say you got a system where like there's 4 motors and they're stored in binary in like memory. You want to turn one of them on or off. You can use these masks to do that. So this is an OR obviously, so this will be 1011 and then exclusive OR, which will be like that. So exclusive OR is used quite a lot in the Vernam cipher. And other encryption. I'm not going to go too much into masks because they're quite easy. And if you didn't get that, you can look at the videos. But yeah, that's bitwise masking.